Hello everyone, today we'll talk about the problem balance a binary search tree. So everybody's favorite topic. Luckily it's not that tough here, we're just given a binary search tree and we want to transform it into another binary search tree which is balanced. And in general, because the definition of balancing is the one that's typically used, when we have a node, it has two subtrees, then the height of those two subtrees, so the largest distance from their root to the leaf, have to be approximately equal. Not always can they be equal, but so we want them to be at most one different. Or in other words, when we go from root to leaf anywhere in the, so let's say in here, the deepest leaf to the left, the deepest leaf to the right, the distances differ by at most one. However, it's also recursive. The same thing is about in the left and right subtree. And that gives us a balanced search tree. And of course, balanced trees are important because then we have a guarantee of logarithmic complexity when we descend the tree. When the tree has n elements, then it has height of about logarithm of n. So how do we balance the tree that we're given? There are many ideas. There are some algorithms that can do it by just rotating the tree, so using left rotation, right rotation, calculating something about the tree and then doing it in place. You can of course simulate any known algorithm for creating a balanced binary search tree. So you have AVL trees, you have black-red trees, and so on. And of course all of those are cursed. Typically you use them, but you use them because they are in your library. And so for instance in STL, and you don't want to implement them yourself. However, I think the best solution here, which is also the simplest, is just to do it by forgetting about the original structure completely and creating the binary search tree that has the same nodes, or if you prefer, the same values, and is a balanced binary search tree. So let's start with looking at the binary search tree and saying what it is. Well, what it is it's a representation of a sorted array, right? It can only represent sorted arrays, and it is just one representation of them. There are many balanced or imbalanced binary search trees, but they just represent the array. So we have A1, A2, A3, and they are all sorted, and we just look at them as if they are a tree. So what we can do is we can first retrieve this array from the binary search that we're given. So this is a standard problem, and we have to perform what is called an in-order traversal. Simply, in order to create, let's say that we have here a subtree representing a subarray in our original array. Then to retrieve that original array, we have to first retrieve the array from our left child, then add ourselves to it, then retrieve the array from the right child. From the definition of a binary search tree, everything smaller than the root is to the left of it, everything larger than the root is to the right of it. And this is exactly what we have to write. Just we have here an order that we want to retrieve. We go to our left child, we append ourselves, we go to our right child, we start at the root, and then after that, in order, we have just the sorted array that our tree was representing. And now we have to, based on that array, create another binary search tree that represents that array and is balanced. Okay, so what order should we insert values in our sorted array such that if we create the tree naively without any automatic balancing, the tree still remains balanced? Because of course, if we just insert elements to our binary search tree, then some binary search tree will be created, and maybe we can just insert them in proper order. And what we can guess, and what is quite simple to understand, because here we have balancing defined by heights. But also balancing means that essentially to the left and to the right of every node, the number of nodes is about the same. It's also congruent with this logarithm definition, because we can look at whenever we go to the left or to the right in a node as a decision that we make. And that decision narrows down the space of possible values that we're looking for. So we want to make sure that at every node, our decision lowers the set of possible values by about 2. And of course, this is why it would be a binary search tree. Of course, an imbalanced binary search tree, which is like, let's say here, right-skewed list. Well, it's not much of a binary search, it's more of a linear search. So yeah, that's why balancing is important. And this property of height, just like the property of size, are both the properties that give us that both those subtrees are about the same size. And so, how can we guarantee that after the first step, so after we choose the root, both the left and right subtree are about the same sizes? Well, it's simple, because if we select a node, then the left subtree would consist of all the elements to the left, the right subtree of all the elements to the right. So we know that we have to start with the middle element. And now this will be the left subtree, and this will be the right subtree. Okay, what now? Well, we want both the left and right subtree to be balanced binary search trees. So we just recurse on left, recurse on right. So we go on left, we go on right. We return the tree that we've created, and that tree will just be the root of the appropriate subtree. And of course, it's easy to implement. Since we have this array defined in our order, we can define a function that operates on that array and takes the bounds from which the elements should be taken to create a tree. So if there are no elements, we create a null node. Otherwise, our root is the middle of the nodes that were given. Now notice here that in order array, I don't keep values, I keep nodes, because if we can modify our tree in order to balance it, then that's essentially a simpler way. We can just modify the nodes themselves, which we keep in an array. So this is our root, and now left and right children are what? Of course, recursion on the left and on the right. If we started with from L to R, and we have a mid, then we take from L to mid minus 1. This is the left. From mid plus 1 to R, this is the right. We return the root, and after that we can just return the tree created from all the nodes that we've gotten previously by traversing the tree in order. And this is probably the simplest solution, and it's actually quite fast. So I recommend you do it like this, but of course there are many other solutions, and if you want to do something tricky with a tree, then feel free to solve this problem in a different way.